Hello everyone, my name is Sandra and today I will be presenting Spinneret, aiding creative ideation through non-obvious concept associations. Mind map is a design tool for various purposes such as comprehension, reflective thinking, and even creativity. Within the context of creativity, mind mapping can be used in divergent thinking where one tries to generate multiple creative solutions for a given problem. For example, in this particular mind map, the user was trying to think of different solutions that can act as a stapler's main function, which is to bind papers or objects together. Here are some of the creative solutions that this particular user came up with. The user thought of crunching papers together or even rolling them up into a bottle in order to bind the papers together. However, as you may imagine, there are some challenges that come about with creative thinking. In particular, the creative process rarely feels linear. There are periods when we burst with inspiration and we feel on top of the world, but chances are there are going to be moments of stagnation and doubt as well. So there is this question of how to deal with stagnation whenever we experience it. A second challenge is design fixation, where one is trying to be creative and come up with new ideas, but their previous knowledge and experience are restricting their imagination. For example, honoring how Kai 2020 was supposed to be held in Hawaii, if you were asked to design a new type of surfboard car rack, there's a good chance the ideas you will create will be influenced by all the surfboard racks you have seen, such as this one, and even this one. Throughout our lived experiences, there are expectations as to what surfboards are and how they should be stored and how even people use them. This influences our thinking. Design fixation can be seen as tunnel vision, regurgitating old ideas, or even being blinded to alternatives. And while a designer may think broadly, certain features of pre-existing solutions can keep reoccurring, as we see in these photos. So this poses as the main challenge of how we can help users overcome design fixation and come up with creative solutions on their own. Researchers in the past have investigated how we can address design fixation with group ideation techniques. In SIGCHI, every team member draws sketches of possible design solutions for a given problem. Each team member starts by drawing a sketch, and then the sketch is passed on to a different team member every couple of minutes. This process continues until everyone's sketches have reached all members. Similarly, 635 brainwriting also utilizes group ideation. Participants write down their ideas on a worksheet and then, like SIGCHI, they will swap their worksheets to a teammate. The teammate will then build upon the written ideas. These work focus on expanding the individual's potential solution space and negating individual biases. However, to the best of our knowledge, there is no team-oriented process on how to address design fixation in mind mapping, and even more so with digital mind maps. Digital mind maps have the benefit compared to traditional hand-drawn mind maps where computational support can aid the design search space by either expanding the search space or even suggesting good design solutions. Yet, most existing digital tools for mind mapping focus on authoring and organization, with little support for addressing the challenges of stagnation and design fixation. Thus, this poses the research question of our work. How can we address the challenges of design fixation and stagnation in digital mind maps? To that end, we created Spinneret, a digital mind mapping tool that uses a functional approach to aid mind mapping. To emulate the mind mapping process, we have provided a series of interactions such as adding and deleting nodes and edges in the mind map. But more importantly, to reduce design fixation and stagnation, we provide suggestions based on the knowledge graph ConceptNet. In the mind mapping process, users write down associations that come to mind as they're building their mind map. Since Spinneret aims to emulate the mind mapping process, in order to reduce design fixation and stagnation, it needs to be powered by an existing knowledge graph based on which associations can be suggested to the user. These suggestions can then potentially inspire a new idea to the user. For example, on the left is a mind map created by a user from our user study. The picture on the right is the zoomed-in version of the highlighted portion of the mind map. If the user is unable to think of new ideas, with Spinneret, the user can click on a node and see suggestions recommended by the user. The picture on the right demonstrates this interaction. The user has clicked on silent mode and has received 5 suggestions that they can either accept or reject. In addition, in order to fully support ideation creation, users are able to add manual nodes to the mind map. If they are inspired by a recommendation, they can add their own ideas to the mind map. The question now to address is how to provide these suggestions. How can we systematically recommend suggestions based on the user selection? Well, ConceptNet can help fulfill this gap. ConceptNet is a knowledge graph that is not domain-specific, and this better represents the general knowledge and concept associations. For example, the picture on the left shows the associations of the concept of computer, and we can see concepts specifically related to computers such as parts of computer and what a computer is typically used for. The domain nonspecificity can help provide concept associations that have the potential to help the user go beyond familiar concept associations and reduce design fixation. To explore the nodes of a neighborhood in ConceptNet, we use the bias random walk with a search bias suggested by Grover et al. In their paper Node to Vec. To demonstrate, let us pretend the selected node is the concept computer. If we define our search bias to be more breadth-first search, the bias random walk would keep the walk local, close to the starting node, and we are more likely to come across associations that are related to computer. In contrast, if we define our search bias to be more depth-first search, the bias random walk is more inclined to visit nodes further away from the starting node, and we come across associations that are not obviously related to computer. We utilize both depth-first search and breadth-first search suggestions in our system in order to support the different creative tasks a user may encounter. For more information about the bias random walk, please refer to the paper. To evaluate Spinneret, we conducted a control study where we recruited 24 participants and they were asked to create mind maps for two tasks, an unconstrained task and a constrained task. The unconstrained task was to create a completely original plot for a short film. The unconstrained task emulates open-ended scenario where the goal is to explore novel ideas. In contrast, the constrained task focuses on generating solutions on how to reduce people's distractions when driving. This task is more restrictive as it requires users to create nodes with more apparent relationships to the existing nodes on the mind map. To study the effect of using Spinneret on the unconstrained and constrained task, we compare Spinneret to a baseline interface. The baseline is a modified version of Spinneret with the same organization and interaction capability. However, the key difference between the two interfaces is that the baseline does not provide any suggestions. It requires the user to create all manual nodes. We chose this approach instead of using existing mind mapping tools in order to reduce confounding effects that may emerge from aspects of the other interfaces. To counterbalance learning effects, we created a 4-task interface combination where participants will either use Spinneret or the baseline for the unconstrained task, and vice versa for the constrained task. From the user studies result, we found that the mind maps created by Spinneret showed a greater diversity of concepts. These 3 mind maps shown here are all produced by the participants from the user study, and these mind maps were created for the constrained task, which is to reduce a driver's distraction. For example, one participant noted dirty windows to be a distraction when driving and provided a solution for drivers to have weekly reminders to clean their windshield. Another participant thought of a legal policy where there would be severe consequences if drivers are caught distracted. Lastly, a participant provided a solution that only allows mellow and slow playing music in the car when driving. But despite the greater diversity of concepts in the mind maps generated with Spinneret, upon qualitative analysis, we found suggestions are perceived differently depending on the task type. For instance, P24 used Spinneret for the unconstrained task, and then at the end of the study, they expressed Spinneret felt like a game. The suggestions inspired the next move, where if the suggestions are too related, they were not interested. This characterization of blue sky thinking was heavily present among participants who similarly used Spinneret for the unconstrained task. In contrast, those who used Spinneret for the constrained task found the suggestions irrelevant and ultimately ended up being dismissed. Observations show that the participants faced multiple unsuccessful attempts to find a suggestion that was more relevant to their task, which is difficult to produce when the task is very specific. This pattern further emerged when we plotted the number of manual nodes versus suggestion nodes participants created in their mind maps with Spinneret. Here, we can see that the participants who use Spinneret for the unconstrained task tend to accept suggestion nodes, in contrast to the other group of participants that relied more on the manual nodes for the constrained task. A second finding indicates that the concept nodes in Spinneret have higher uniqueness compared to those in the baseline. However, when we analyze the mind maps with respect to network measures such as the number of nodes or even the depth of a mind map, We found that there was no significant difference when comparing the mind maps produced by the baseline and Spinneret. This finding is particularly interesting because Leeds et al. In their 2019 work reported that in order to generate more distinct concept nodes, users need to create a higher number of nodes and create mind maps with a greater depth. This difference may be due to Spinneret providing non-obvious suggestions early. This prompts the user to explore more unusual ideas that may otherwise take longer to reach or even not at all. In fact, this is supported by 83% of the participants who agreed or strongly agreed that regardless of the task for which they used Spinneret, the tool prompted them to think of ideas that they would have not otherwise considered. This indicates that Spinneret does indeed help reduce design fixation. To conclude, we have presented Spinneret, a digital mind mapping tool that aids creative mind mapping by providing non-obvious suggestions to selected concept nodes. This was achieved by a bias random walk with depth first search and breadth first search biases on a knowledge graph to generate suggestions. From our study, we found that the mind maps generated using Spinneret showed a greater diversity of concepts. Concept nodes showed a higher uniqueness across participants in the Spinneret condition. Lastly, Spinneret suggestions were better received for the unconstrained task than for the constrained task regardless of the search bias applied. Thank you for watching.